Hello there, Mr. Sutton here with the Pre-Cal Honors 2-7 Part 2 homework solutions on applications of polynomials. For this problem, we have a manufacturer of cardboard boxes with a rectangular piece of cardboard that's 67 by 70, and he's cutting out identical squares from each corner of the cardboard and then folding up the sides and making a box without a lid. So here's a visual of what's going on. Here's our rectangular piece of cardboard, cutting out squares from each corner, folding up the sides. So you get a box that way. We want a formula for the volume of this box, its domain, the size of the squares, and the maximum volume. So let's start with the formula. To get a formula, in general, the formula for a volume of a box is length times width times height. But we need to get everything in terms of one variable to do all this other stuff. So let's try and express everything in terms of one variable. We'll let x be the length of these squares because that's what we have control over, is how far we go in before we cut out these squares. And we can use that to get the other two dimensions. This x distance here is actually going to be the height of your box when you fold up the sides. The length is going to be this leftover bit that isn't lost when you cut out these squares. So let's say that this is the 67 side and this is the 70-inch side right here. On the 67 side, after you cut out these two x squares, you've got 67 minus 2x left over for this folded up side. And by the same token, over here, you've got 70 minus 2x left over for this folded up side. So now with our volume, length times width times height, we can rewrite that with these expressions now. So 67 minus 2x times 70 minus 2x times x. And to get anything else here, I'm going to need the domain anyway. But to get the domain, I'm going to need the roots of this equation because this is an equation that only makes sense if you get values for the volume that are bigger than 0. So let's figure out where this thing equals 0, and that'll tell us what x values are okay to plug in. So going from left to right and zeroing out each of these parentheses, 67 minus 2x, if that equals 0, adding 2x and then dividing by 2 gives us, let's see here, that'll be 33.5. 70 minus 2x, we have an x value of 35 out of that zeroes that out. And then this x over here is giving us an x value of 0 for a root. So when you have 0, that's going to zero out the height. So we can't go 0 or lower than 0, or else we'll have no volume. When we get to 33.5, that's going to zero out this length side here. So that's kind of our max possible x value that we could plug in is 33.5, or actually a little bit less than that. And if we go even bigger than that, we get negative numbers for volume, which is no good. So our domain then is going to be from 0 to 33.5. And now we wanted the size of the squares that maximizes the volume and the volume itself. To get the x value, the size of the squares that maxes the volume, we have to use our calculator, the fmax function. So what I'm going to plug in on my calculator is going to be fmax of my volume formula, which I'm going to store as y1. Then I'm going to write an x and my domain numbers 0 and 33.5. Let's go to the calculator and do this now. So I'm in my y equals on the calculator. I've entered my volume formula as y1, so now I can pull up y1 and get this whole formula whenever I want. Let me quit out of there, and let me do math, and then 7 is going to give us fmax. And I'm going to go to alpha trace and click enter to get y1 out of that, so that's the formula I just stored. Let me now do comma, x, comma, and then my two domain values, 0 and 33.5, and close the parentheses. This gives me the x value 11.41 if I round that off, and that's in inches. So that's the size of the squares that's going to maximize my volume. To get the actual volume, I have to go back to the calculator and actually plug this answer in to my volume formula that I stored as y1. So let me do alpha trace and get y1 back. This time I'm going to open a parentheses and plug into it the answer I just got. So I'll do second answer down here, and that gives me roughly 23,783.15, and that's going to be in cubic inches. This problem is one of these fold up the box sort of problems. We've got a rectangular piece of cardboard, measures 40 by 45 centimeters. We're cutting squares out of the corners and folding up the sides to get a box that doesn't have a lid. We want a formula for the volume, the domain, the size of the squares, and the max volume for this thing. So a bunch of information. My volume formula in general is going to be length times width times height, but I can't have three different variables. I need to express everything in terms of one variable. So I'm going to let my variable x represent the length of these squares that we're cutting out, because I can base everything else off of that one piece of information. So for volume, we need a length, a width, and a height. We've already got the height expressed. X, the length of these squares, is going to be how tall your box is when you fold up these sides. To get the length and the width, I have to look at these sides that we're actually folding up after you cut the squares out. This side up here, which let's just say that was the 40 centimeter side, after I cut out those 2x squares, I now have 40 minus 2x left over on that side. On this other side, I have 45 minus 2x. So for my volume formula, length times width times height, I can write 40 minus 2x times 45 minus 2x times my height that I said was going to be x. All right, so to get the domain for this, the x values I'm allowed to plug in, those are basically going to be x values that give me a positive volume when I plug them in. There are some x values that will either give me 0 for volume or a negative volume that I do not want to plug in. So to figure out which is which, I'm going to zero out this whole function and find the roots. And then I'm going to see where between those roots I get positive and negative numbers. So going from left to right and finding the roots, if I want to zero out this first parentheses, I need to plug in an x value of 20. And then for this next one, 45 divided by 2 is going to give me 22.5. And then this x, if we plug in 0 for this x, that zeroes out the whole volume. So if I have 0 plugged in, that zeroes out my height, just talking about this in real life terms. So we don't want to have 0 or less than 0. And if we get to 20, by the time I reach 20, these squares are so big that I've lost this entire length side here as well. So if I get to 20 or higher, that also is no good. And this other side's kind of irrelevant because I've already lost this side by the time I have squares big enough to lose this side. So my domain then is going to be the smaller of these two. It's going to be 0 to 20, not including those numbers. And this is actually going to help me now find the next two pieces of information, the size of the squares and the max volume. To get the size of the squares, I have to use the fmax function on my calculator. So I'm going to put in fmax, and I'll show you that on the calculator in just a sec. The things I'm going to plug in there are the volume function, which I'm going to store as y1 when I use this fmax function. I have to write x, just x every time when I do this function. And I need my domain numbers 0 and 20. Let's go ahead and look at how this looks on the calculator now. So here I am in my calculator, and I did y equals, and off camera I entered my volume formula with all those parentheses and this little x at the end into my y1. I'm now going to quit out of that, and I'm going to do the fmax function. That's going to be math 7. And I have to pull back y1 where I stored the function, so I'll do alpha trace, and then I've got the y1 already pulled up in that menu. And then let me do a comma, x, comma, and then 0, comma, 20. And then pressing enter gives me the x value, roughly 7.05. So that's going to be in centimeters, and that's the length of these squares that maximizes my volume. But now to get the volume itself, I have to go back to the calculator and actually plug this number into my y1, into my volume formula. So let me do alpha trace y1 again, and this time when I pull up my function, I'm going to open a parentheses and plug in the answer I just got. So to do that, I can just do second negative sign, which gives me answer. That's the last output I got. Pressing enter, I get 5,642.19, and that's going to be cubic centimeters. For this problem, we have a box with no top built by taking a 23 by 39 inch sheet of cardboard, cutting out squares from the corners, and folding up the sides. So here's our rectangular cardboard with the squares cut out of the corners, and we're folding up those sides to make a box with no top. We want the dimensions of the square that yield the maximum volume. All right, so to figure this out, we have to get a volume formula and figure out the value that maximizes that volume formula. But since volume is length times width times height, that's 3 different quantities. I want to express all of those as a single quantity, namely the dimensions, the length of the square that's going to maximize that formula. So let me start by letting x be the length of my squares here, and I can express all the other dimensions of my box in terms of x. So when I fold up the sides, x is actually going to be the height of the box. And the length of the box is going to be whatever this side is when I fold it up. So initially we had 23 inches on this side, or this side. I guess it doesn't really matter, but we have to pick one and go with it. So let's say I had 23 inches here. I lost an x over here and another x here. So that's 2x that I have to subtract from my initial 23 inches. For this side here, when I fold it up, I'm going to have 39 minus the 2x squares that I just lost. So for my volume formula that I'm going to use, length times width times height, I can actually write that now as 23 minus 2x times 39 minus 2x times this x that we were letting represent the height. To get the formula on my calculator, well, I mean, I can put this on my calculator, but in order to find the x value that maximizes it, I need to tell the calculator where to look for x values. I need the domain of this function. So let me go ahead and figure out what's going to zero out this function, because domain for one of these problems basically means all the x values that give you a positive volume when you plug them in. So finding the roots of this formula here, this equation, this expression, going from left to right and zeroing out each parentheses, for my first parentheses, if I add 2x and then divide by 2, we get x equaling 11.5. That zeroes out my first parentheses. The next parentheses gets zeroed out when x is 14.5, or actually 19.5, I should say. And then 0 is going to zero out everything because of this x here. So my domain, the x's that it's okay to plug in, the lowest x value that I could possibly plug in is 0. Because once I do that, I have a height of 0 and a volume of 0, and we don't want that. So I have to be bigger than 0. When I get to 11.5, I've used up this entire side up here, which again leaves me with 0 for one of my dimensions and 0 for the volume. So I can't get any bigger than 11.5 for these squares. So my square sizes have to stay between 0 and 11.5. Otherwise, I get 0 or I get a negative volume when I plug them in this formula. So now that I've got my domain, I'm going to go on my calculator and use the fmax function as follows. So I'm going to put my volume function, which I'm going to enter as y1 in the calculator, into the fmax function, along with x, which I always write, and my domain numbers 0 and 11.5. Let's go ahead and do all that now. So on my calculator, I have gone to the y equals and entered this volume formula into my y1 so that I can use it as many times as I want. Next, let me quit out of there. And I'm actually going to use y1 like I've written on the screen here. I'm going to go to math and then 7 to get fmax. And to get y1, I do alpha trace, and that pulls up a little menu, and I can select y1, press enter there. And now let me do comma x, comma 0, comma 11.5 for my domain that I'm plugging in. And this tells the calculator to look for the best value of x between 0 and 11.5, which is, if I press enter, about 4.67, and that's going to be in inches. So that's the size of the squares, the dimension of the square that maximizes my volume. They didn't ask for the actual volume, so I get to stop here and move on with my life. On this problem, we're making an open box by using a 24 by 24 square sheet of metal and cutting out squares from the 4 corners to fold up the sides. So here's our sheet metal in a square. We're cutting out more squares from the corners, folding up the sides. We want to know the size of these squares, the little squares that we're cutting out, that will yield the maximum volume. So if we're talking volume, we're talking length times width times height, if we're dealing with a rectangular prism here, a box. But to get anything useful out of volume, I need to express everything in terms of one variable, like x. So to help me out here, I'm going to let x be the length of these squares. That's the thing I'm trying to figure out anyway, the size of the squares, the length of the squares that's going to give me the best volume. When I fold up the box, this x here is actually going to be the height of the box. Now, I need the other dimensions expressed in terms of x. So this length, this side here when I fold up the squares, that's going to be the length of the box. To get that length, I'm starting with 24 inches over here, but then I'm losing this x and another x, 2x's from that 24 inches. So I can write 24 minus 2x for the actual length when I fold up this side. And by the same token, the 24-inch side of the sheet metal over here just lost 2x when I took out these squares. So we have another 24 minus 2x for this width dimension as well. So using my volume formula, length times width times height, I can write the volume now as 24 minus 2x times another 24 minus 2x times x. And if I wanted to, I could just write 24 minus 2x quantity squared times x. I don't actually have to write that twice. Let me go ahead now and find the domain, because I'm going to need that for my calculator to tell my calculator where to look for answers. So the domain, those are going to be the good x values that give me positive volumes, and those are going to be between x values that zero out the volume. So just finding the roots, because that's what zeroes out this thing, is the roots of the equation. Setting these all equal to 0 and solving, this first parentheses is going to be 0 if x equals 12. Same thing with the second parentheses. And if x equals 0, that zeroes out this x, which zeroes out the whole volume. So if I plug in 0, I've got a height of 0, a volume of 0, and that's no good. If I plug in 12, if that's the length of the squares, then I've used up this side and actually also this side, and I again have a volume of 0. So my domain has to reside between 0 and 12. So now that I've got this information, I'm going to go to Fmax on my calculator, and what I'm going to plug in is my function here, which I'm going to store as y1 in a moment, and then I always use just x, the letter x, and 0 and 12, my domain numbers. Let me show you what that looks like. So here I am in my calculator. I went to the y equals, and I'm entering this function as y1. And notice on here I got a little bit lazy and just wrote 24 minus 2x parentheses squared. I didn't feel like writing it twice. And then I've got that little x at the end. So quitting out of there, I have to go now to Math 7 to get the Fmax function. And to pull up y1 without writing all of that again, let me do alpha trace, and that gives me my y equals menu. y1 is already selected, so I press enter, and now I don't have to write all that stuff again. And let me do a comma x, comma 0, comma 12. And pressing enter, that gives me an x value of 3.999999, which basically is 4. So 4 inches then is the length of squares that's going to give us the best volume. And they didn't ask for the actual volume, so this answer is complete. For this problem, we're making an open box from a 7 by 56 foot rectangular piece of sheet metal. This is going to be a big box here. By cutting out squares equal size from the 4 corners and bending up the sides. So here's a visual of what's going on. We've got this ginormous piece of sheet metal, and we're cutting out these squares from the corners and making a box out of that. So we want the maximum volume the box can have. In general, the volume of a box, rectangular prism box, is going to be length times width times height. Unfortunately, that's 3 different things. We need just one variable to express everything, at least if I want to get my calculator involved and help me find the max. So to do that, I'm going to let x, my variable, represent the length of these squares that I'm cutting out here. Now when I fold up these sides, this x, this square length, is actually also going to be the height of the box. So this gives us one of our 3 dimensions that we need expressed in terms of x. We also need the length and the width expressed in terms of x. Now the length, we could think of that as this side right here, I guess, when we fold up these sides. Initially this was 7 feet from one end to the other, but we lost these 2x squares. So now we only have 7 minus 2x when we fold up that side. And over here, the width of this box. Initially we had 56 feet, but now we lost 2x, so now we have 56 minus 2x for that dimension. So when I actually write my volume formula, length times width times height, I can now write that as 7 minus 2x times 56 minus 2x times this height of x. And before I plug that in the calculator and find the max, I also need to find the domain because my calculator needs to know which x values to actually look between when it uses the fmax function. So my domain, those are going to be the x values that give me positive volumes when I plug them in. To figure that out, I'm just going to find the values that zero out my function, the roots of my function, and then I'll figure out which of those values are going to give me the domain. So going left to right, zeroing out each parentheses, this first parentheses gets zeroed out if x is 3.5, 7 divided by 2. For this next parentheses, an x value of 28, we'll zero this one out. And this last x, if that's 0, then the whole volume gets zeroed out. So if x is 0, I have a height of 0, which means I basically don't have a box. If 3.5 is the length of these squares, then that means that I've used up this entire length side here, and I no longer have a length, and again, no box. So my x values have to be between 0 and 3.5 for this function to make any sense. It's going to be a while before we zero out this side here, but this root of 28 doesn't really tell us anything useful because by the time I get close to zeroing that out, I've already more than zeroed out this length side. Anyway, on the calculator, I'm going to be doing fmax of my function, which I'm going to store as y1. Then I'm going to write an x, and then I'll use my domain numbers 0 and 3.5. So let's go ahead and do that. Here I am on the calculator in the y equals menu, where I have entered this volume formula as y1. Now that I've done that, I'm going to quit out of there. So now whenever I call up y1, I get my function, and I don't have to write it over again. I'm going to now use the fmax function that I wrote here. So to get that on the calculator, we do math 7. And then to get y1, we have to do alpha trace. And that gives us a menu of our y equals. We've already got y1 selected, so let's press enter. And then let me do a 0, and I just will literally write x, and another comma, and 0, and 3.5. And then if I press enter on all that stuff, I get 1.69-ish. That's going to be in feet. So this is the length of squares that maximizes my volume. But they didn't want that. They wanted the maximum volume itself. So make sure you go back and read the question and make sure you're answering the actual question. So going back to the calculator, to get the volume, I have to take the volume maximizing x value that I just found and plug it into the volume formula, which we conveniently already stored as y1. So to get y1, again, I do alpha trace and click on y1, or press enter when it's selected. And now I'm going to open a parentheses to plug things into it. I want to plug in this number that I just got, so I'm going to do second answer, and I can close the parentheses if I want. Pressing enter now gives me about 321.92, and that's going to be in cubic feet for the max possible volume.